Record has started. Right, should be fine, right? Okay, let's continue our lecture. I guess everything's ready now. Good, which means that I cannot change my computer. Personally, I think MacBook Pro with the bar. Do you know that the bar with the display bar is the worst version I have ever seen in MacBook. Please don't buy this. Maybe Apple maybe give up this design. It's the worst worst MacBook Pro I have ever seen. 就是那个有那个 Touch Bar 那个有那个会显示的那个 MacBook Pro 超烂的啊！这是我有买过最后悔的一个笔电。它那个 bar 又很难用，它的键盘又是最烂的啊，所以我很后悔买这一台啊。不过之后他们就没有用这个 design， 所以他们应该也知道这很烂吧。Okay, I believe this out like 2019 or 2020. I don't know. Been better now. All right, so let's continue our lecture. Thanks for coming. Morning. And last time we talked about the definition of the thermodynamics of solids, and we introduced some terminologies. And then we had really quick review about the classical thermodynamics, which is we are going to do last time and this time. And oh, by the way, there will be a really important announcement now because I'm going to on the business trip next Wednesday. Sorry, next week, entire week. I need to go to several universities in the US, MIT, UIUC, Brown University, and Northwestern. Okay, so I need to go with other 6 professors in material science and engineering field for 1 week. So next week I cannot do the instruction. So next week we don't have any lectures. Okay, so 我下礼拜要跟6位教授去材料系的教授，台湾的材料系的教授去美国4个大学，然后我们要参访要去推广我们台湾的材料系的合作吧，哈。那所以下礼拜我没有办法上课，那下礼拜没有课，那就是我很怕16周是没办法上完所有的课程，所以说当然之后也会有几次就是例如说我要帮忙学，就是系上面试啊或者其他的事情，所以可能会有大概再2次，就是我无法上课，礼拜3的时候。那但是我很怕16周就是这么多就是无法上课的状况，所以我会到时候啦，如果我发现没办法的话，我就会用网络就是 YouTube 直接 share 给你的形式，这样其实跟现在讲都差不多了哈。只是一个是现场，一个是之前的上课，那就是怕说上不完，那所以可能到时候就会以这样的方式。但是现在才一开始嘛，之后可能还可以再追回来，所以下个礼拜就是真的就是没有上课。好，就这样。So I just want to say that I'm afraid maybe 16 week may be not enough for all the entire course. So if next time I need to have a business trip or other stuff, I cannot give the lecture. I may just give you the video that I gave last year, and then to make the progress finished by the deadline. Okay, so that's it. Next week we don't have any lecture. All right. So I will also announce this in Facebook as well. Right. And then last time we talked about some terminology, like first law, d bar Q equal to du plus d bar W, And this is work. Work are related to, oh, so also please be careful about the side convention. Side convention actually has no meaning, but just the rule that this textbook choose. Okay, so we just follow, every one of us follow this, and then you will be able to have better performance in your exam. Okay, and then the bar W greater less than 0, which means that work done on the system, and greater than 0 done by the system. And it's natural to choose to regard the work as the function of P and V, right? Because it's all related to the volume change and the pressure, right? And last time I guess we finished here, right? We talk about various examples of work that not only suitable for ideal gas, also suitable for the application used, studied in your lab, right? So there are several advanced material, more advanced than ideal gas, right? So some of your lab may be working on film or magnetic material or dielectric material. So they all has their own form of work. So all we need to do is we need to find the intensive variable and extensive variable and times them not together, multiply them together, it will become the work. Okay, so although the knowledge we learn in this textbook are all related to gas or solid, of very fundamental, but the concepts are general enough to apply to any other advanced materials that you do, that you and your lab and your professor, your supervisors do. Okay, and there's a very important part here is differential of the W is inexact. Inexact means that the change, the difference of the W, we need to need to have a bar on it, which means that the W depends on the path. Okay, you can see this because the work is actually the area underneath of the figures that constructed by your intensive variable and extensive variable P and V, right, in the ideal gas part. So you see that different paths create different areas, which means that they are depending on the path, and then you can see the difference of two paths indicating the energy loss. Okay, so for example, this is ferroelectric materials. Actually, my study in my PhD degree, and ferroelectric material can be applied for to be one of application is the memory devices. So the material should be PZT or ferrotitanium, and the key feature will be the spontaneous polarization and the ability to reorientate its polarization. Okay, for example, actually I need to did this. Okay, so you can imagine that there are polarization in the ferroelectric material marked in blue. Okay, blue material. If you apply electric field, it will the electric field will make the polarization in each crystal align to the direction of you applied electric field. So it can change their orientation. Okay, and so which means that if you have positive electric field, it will switch up, and then if you have negative electric field, it will switch down. So you can see the polarization can be up and down and positive and negative. So you can see this hysteresis loop, special hysteresis loop. So you can see that this is actually very similar to the figure here, PV. Now it's a PV, but next in the next page, EP, EP, right? So very similar, and but different material, this is ferroelectric, this is ideal gas, right? So different material will give you different plot of the work plot. So you see, of course, this is the energy loss. We examined energy loss. Okay, right. So you see that this is not really perfect mirroring. I just project the entire screen. What I see, you see that on the screen. So this is not really ideal. I'm sorry, but I don't know why I cannot find the proper projection option. Right. Anyway, just saying that. So thermodynamics actually helped me to obtain my PhD degree when I do my PhD degree, and because I'm doing simulation, so I just write down all the thermodynamics into the programming code, and it can help me to simulate the structure, inner microstructure, and to perform this shape. Okay, it's actually in my thesis. Quite fun when I was young, like 15 years ago. Yeah, wow. OK， 我只要跟大家讲，就是说这个是铁链材料，是我小时候不是博士的时候在研究的材料，然后那个材料它是PET 或者是 Barren Titanate， 我也不知道中文怎么翻译哈，总之它就是一个材料，然后它可以做成记忆体，然后它的有几个特点，就是它里面天生就会有一些极化量的产生，那极化量不止还会产生，它还会跟随着外力去变动它的方向。例如说，你电场加上去，它就会往上；电场加下去，它就会往扭转下去。这样，那这张图其实就是它的十字曲线，它的 electric field 跟 polarization 就是极化量跟电压，就是就是可以把它写成想象成跟那个 PV 图是一模一样的东西。好，那当然 P 跟 V 在这个材料里面就已经不是很重要了，好，反而是 PE 比较重要。那这张图你对它做 electric field， 它就有 polarization 的改变，然后你画这张图以后，你就会发现它会有一个面积的路径，它的线就会围绕出一个路径，那就是我们刚刚看到的 energy loss。所以其实这个东西跟之前的ideal gas 的 PV 图是完全一样的概念的。那虽然它看起来非常的进阶的材料，但是它终究脱离不了古代的这种概念。那它就真的帮助我那时候，因为我在写程式，那我是做模拟的，所以我就把这些 thermodynamics 的 equation 啊，就真的去把它写下来，用程式去写下来，去做一些微分、积分等等的，我就可以去模拟这个材料它的内部的行为、微结构要怎么长，这样子还蛮有趣的。Okay, so just let you know examples that maybe although it looks like not familiar, not related to what you've done in your lab, but actually they do. Okay, they are correlated. Right. Next, internal energy. Internal energy is very fundamental. Everyone has energy in you. Everyone is energy. Okay? Everything is energy in this universe. Okay. So when you exist in this world, we have some energy in us. This is really interesting because when you get old, like when you have middle age crisis, which I have that at the moment, you will feel that everything you try to doubt why you are here and what's your purpose in the world. So sometimes you will read a lot of book, and then you will find out a book will tell you you exist and your energy and everything are the same. We are the one, something like that. But it's really interesting that when you get old, you think too much. Maybe, yeah. Well, 刚刚讲一讲，开始想到，我最近也看到书啊，或什么之类的，常常就会，尤其是在大家变老了以后， 未来哈，大概像我这个岁数的时候，就会有中年危机啊。那中年危机什么意思呢？就是当中年危机，我就是最近都在看书了哈，就是对于心理的那个状态都会有一些影响。那跟大家分享哈，就是当你到了一定的年纪以后，以前没有想到的事情，就会开始想到，你就会想到你为什么要生存在这个世界上。或许搞不好你们已经在想到了，哦，因为现在年轻人都很早熟。但我真的是就是看，就到40几岁的时候，觉得就是我到底在干嘛这样。然后以前都没有在想这些事情的，现在都开始想这样。那书就会告诉你你是我们都是能量的产生啊，然后灵性啊，然后打坐啊、静心啊，什么什么的，我觉得是还蛮有趣的哈，就是你就会发现一些你想要找的答案，哇，你很想要找答案，但你找不到，这样很悬吧？我小时候我也不觉得会这样，但是每个人都会有一种必经之路，还蛮有趣的。那需要自己去解决自己的课题。对，小时候觉得自己是特别的，但是其实没有，其实都不特别，好，大家都差不多，好，对，就这样，好了，没事，就是有感而发，尤其是呃生活的压力啊等等的，你就会更想要就知道一些你生存的意义是什么，这样，对，好，有时候跟你们聊，就是讲一讲也算是抒发自己的情绪，不过我觉得看书是一个看书跟运动是一个很好的方式，就是如果今天就是状态不是很好的话，那就靠这2件事情来帮助你这样。Anyway, just saying that reading book and doing exercise quite important for myself for nowadays recently 2 or 3 years because I getting old I guess and then everything's different so may kind of remind you focus on your mental health. Okay, this is important. Right. I don't know why I say this, but internal energy. Too far. I get too far here. Right. Internal energy is that uh, well, the definition is actually the du is the negative of the adiabatic work done by the system. So I guess this is obvious, right? Adiabatic means that there's no heat flow into and out of the system. So d bar Q equal to 0. So of course, du equal to negative d bar W. All right? So just follow the equation. So what is internal energy? Internal energy is the total energy contained by a thermodynamics system. Me and you are also a thermodynamic system, right? We have some internal energy U inside us. It is the energy needed to create the system, but exclude the energy associated with its movement. So which means that if you exist in this world, you have your internal energy in it. So in the exam, you can also think if you have material that definitely has some internal energy in it. If you add in more materials in the system, you means also adding internal energy into it. So internal energy will be increased, and then we will discuss this later. All right. The internal energy is a state function. State function. State function, which is independent of the path. So you can see the du here has no bar compared to w because d is independent of the path. So it's describing the point at the state. Okay, each state has its own internal energy. So if you have the same state, you will have the same internal energy. It describes specifically that point, that state. And then it is nature to choose the U here, and as a function of V and T. Why? Because if we take an example of the ideal gas, you can see there is a if there is a so if there is a container with a piston and you have gas inside and you have a volume temperature describing the ideal gas condition state in that moment, at that moment, if you heat it up, right? If you heat it up and if you heat it up, of course, it will change its volume and your V and T will change, right? So which means that, you see, your internal energy, if this is, well, I mean, if you change you give the temperature heated up, your internal energy also increase. So you can imagine that this is a really straightforward. If you want to increase the energy of the system, you just just heat it up, and you can see the volume and temperature is really specific parameters for us to describing the internal energy. So it's nature to choose the function U as a function of V and T. But of course, again, you can change other P or other parameters to describe it. It's okay. But nature, if this is one straightforward way to do that, is choosing V and T. OK， 内能，内能其实它的定义就是说，当一个东西存在的话，它就一定会有能量。所以如果你在一个系统上加其他的东西进去，加新的东西进去，你整体的内能都会提升，这是很正常的事情。那 internal energy 内能它是一个 state function， 这个 state function 的意思就是说，它可以去叙述这个状态。那这个状态跟这个状态，其他的状态跟路径是没有关系的，它就是描述那一个点。OK， 所以它跟路径是没有关系的。然后还有什么？哦，然后它后面又说，很自然的，我们的 U 其实可以选择成就是 V 跟 T 的函式。所以这边可以看到，很自然的，如果今天有一个 ideal gas 在那边，你加热它，当然内能就获取了它的内能嘛，对不对？它能量就变多了，那体积当然也会同时变化。那所以这时候我们很自然的就会把它写成是说，就我们去描述这个内能的状态，通常都会很直觉的用 V 跟 T 来表示。还是一样还是一句老话，就是说你可以用别的方式去描述它也可以，但是它通常都是会经过第二次的转换才会到 U 这边 P U 啊什么之类的。所以说都可以，只是很自然的第一步想的就是 VT 拿来当做是改变 U 的最直接的一个方法，就是你在实验上也是这样去改它的啊。那你要去用压力去改它的内能，也可以，但是你就必须比较经过一些转换。但是 V 跟 T 就是很最直接的去修正它，这样子。Okay, so let's continue another terminology introduction. Heat is the Q, which is also depending on the path. So the bar Q with the bar here. Okay, and energy flow between a system that is surrounding due to temperature difference. Okay, high to low, of course, across the boundary, and a finite thermal conductivity of the boundary. It is defined to be positive when heat flows to the system from surrounding. This is quite important. Okay, so I will give you sign convention here. If debug Q greater than 0, heat flow into the system. Debug Q less or equal to less than 0, heat out of the system. Be careful. Be careful. This debug Q sign convention is, if I remember correctly, it is different from students or teacher taught in the Department of Chemistry, okay, or applied chemistries. Okay, so they may has inverse sign convention. They say debug Q less than 0 is heat flow into the system in chemistry department. Okay, careful. So if you are a student graduated from that, please be careful about this because 10 years ago, 5 or 6 years ago, there are students graduate from that department, and then he asked me, did I talk wrong? Did I teach wrong, incorrectly? Because their teacher taught debug Q greater than 0 is heat flow out of the system. So they're kind of different. But both of us are correct. But this sign convention is chosen by our textbook. So please be careful. This is kind of the rule that we choose to follow. Okay, both are right, both are correct, but we need to be careful. All right, so heat is not a state variable. Yeah, because you see there is a bar. So you can imagine that if you maintaining the U, if you do the cyclic process, which means that the initial condition and final condition are all the same. Initial condition equal to final state, which means that du equal to 0. So which means that debug Q and debug W actually are the same. So you can imagine that they actually has equivalent characteristic to U, to internal energy U. Okay, because you see they actually, if you the internal energy doesn't change. Actually, they are interchangeable. They're actually equilibrium. So heat and work are equivalent in the sense of changing in the internal energy. So to internal energy, debug Q and debug W, they are similar things. OK， 好，这边要讲的是热。热的话呢，实际上跟供气跟 work 是非常非常像的。那就这边就是一个例子。因为 U 是 state variable 嘛，对不对 ？state function。所以当你做一个 cyclic process， 就是做一个过程是初始跟结束都是一样的状态的时候，表示说它的 du 不会变哦，对不对？因为它是同一个点。那表示说这时候它的 u 不会变的话 ，debug q 跟 debug w 其实是一模一样的事情。所以说，在对于改变 internal energy 内能这件事情来说，热跟供其实是完全一样的。对于 internal energy 来讲，热跟供其实是一模一样的东西。那这边的 sign convention 要很注意哦。debug q 大于0的话是热流进去 system，debug q 小于0的话是热流出 system。这有点危险，因为也不是危险啊，就是说我们要小心一点。就是在5、6年前有一个化学系的，还是化工还是硬化系的同学毕业了，来到这边，然后他就是在修这门课，然后说：“老师，这边你教错了吧？以前我们老师都说这是反过来的。”哎，对对对，大家都对啊，只是课本采取的 convention 是不一样的，要小心哦。化工系那边他们是小于0是 into， 然后大于0是 out of， 我这边要小心。所以我们在这边就使用这个吧，好不好？就是用课本上大家都使用同样的语言、同样的规则，这样比较好。Okay, so let's continue. After we've introducing the basic terminology, we are going to do some calculation. The calculation of work. d bar W equal to d bar Q minus du. I guess we just change a little bit, it's changing around. And then we know that PdV equal to, well, sorry, I should make it capital. D bar Q minus du. All right, so this is the first transformation. Good. And then for reversible process, d bar W equal to PdV. So that's what I wrote here. Okay. Of course, this is reversible process means that we are going to considering ideal condition. Okay, so d bar W can be written as PdV. And so let's continue because we want to see how we change the volume, So we regarding that in this system, in this ideal gas system, how can we changing the volume of the gas? Easy. If we do the experiment, or either change the pressure, either change the temperature. So we treat the volume as a function of T and P, and we see how we change this will change the volume. How we change the pressure will how much will it change the volume. So we can see that there will be two contributions. The changing of V can have two contributions. The first one is change of T. The other is change of P. So you can imagine that this is actually a slope. The coefficient in front of dt is actually a slope. What does that mean? Which means that if you have a V1 T1 condition, if you have V1 T1 condition, and then you either change you can change dt and to see how much it changed dV to make it V2 to T2. Okay, so actually you want to see how temperature change will change volume. This is one contribution. So this is actually a slope. So you can imagine that this one is actually this, right? Partial V, partial T. And although I write D and DT and DV, actually we didn't consider the pressure, right? So here we actually can say partial for the constant P. Constant. Okay, so you have a subscript in the coefficient means that at that slope we didn't consider the other coefficient. Okay. Similarly, if here this slope, this coefficient is the second contribution. The second contribution is how you change the P will change dV. Okay, so this is also the slope, right? So that's it. Two contribution to change dV, to change V, dt or P, and then sum up together, it will be right. It will be the contribution will be from these two. So then we can substitute. Let's see. Let me take a look. Okay. So then we want to find this solution. Actually, they can be measured. They can be measured, right? When you do the experiment, you can measure this. Measure this. But it typically you need to if we do some kind of trick, we want to see it actually related to the actual value of V at the current V. So if we divide by V and time V, it will cancel each other out, right? Cancel each other out, and then we can directly obtain this value from the experiment. Okay, so we say that this is we say this expensivity beta, and the other we name it kappa. It's called isothermal compressibility. Why we want to do that? Because we can measure it by experiment. Okay, so I can write down this the definition. Is that coefficient of the volume expansion fraction change of the volume due to temperature at constant P. Okay? Okay? And the right-hand side is that very similar is fractional change under pressure at constant temperature. Okay, maybe you will think why we bother to divide the current volumes here. Why? Because the current volume is actually depending on that case. But now if you divide by V, which means that you have a fractional. So you see that it's not depending at volume anymore. So you can treat that as a material properties. Not depending on the volume, right? If you just directly get this, you didn't divide by volume. It will depending on the case. But if you divide by volume, which means that it doesn't relate to volume, so it becomes a specific value, and then it can be material properties. It's become universal. It becomes general. So that's the reason why we get rid of the volume by dividing them. And then this beta can be treated as a material properties for expensivity, and this definition is a fractional change of the volume due to temperature at constant P. So it's very similar to what you know about the CTE, right? The thermal expansion coefficient, something like that. And isothermal compressibility is also a fractional change at due to the pressure at constant T. All right. So these two are some sort of material properties that you can measure in the experiment. Okay. Now let's continue. The bar W equal to beta PV dt minus Sorry, I read it too big. d bar W equal to beta PV dt minus kappa PV dP. And then it is really useful for determining the work done in the compressing or expanding a solid under different condition, either under constant temperature or constant pressure. 好，那我们就来就是做一些计算，对于功的计算。d bar W 如果我们今天把它看成是 reverse process 的话，那它就可以写成 P dV。当然 reverse process 是比较 ideal 的状态 ，ideal gas 的状态。那我们把它写成 P dV 的话呢，不是 ideal 状态，不是 ideal gas 状态，是 ideal 的状态，是 ideal 的状态。好，那改变它的 P，改变它的 V 的话，它就会有去压它、去拉它，对不对？好，所以它就会改变它的，就做功在它身上的意思。写成 P dV 以后呢，我们就想要看看这个 V dV 要怎么样去改变它。那要怎么改变？很容易啊，就是要么就加温，要么就加压嘛，哈。好，那加温加压的话呢，它改变它的体积有两种贡献，一种贡献是改变温度，它会改变多少？改变压力，体积会改变多少？有两种贡献。那这样子分别的贡献呢，可以想象是它的斜率，这个系数就是它的斜率的意思。那这边就是改变底梯，它会有多少的改变体积？那另外一张图也是改变压力会有改变多少体积？那这边就是它的两个斜率。那我们把它写在这里。这时候呢，我们就把它乘上 v 除上 v。可能同学可能觉得很奇怪，为什么要做这件事情？原因是因为如果不把它除上 v 的话，它就会跟你当下的 case 的体积大小扯上关系，就不会是一个材料参数了。你把它体积除上去，它就是跟体积没有关系，它是一个比值的关系，所以可以应用到所有的体积上面。那这就是变成材料参数的一个，就是用这样的 trick 就给它变成材料参数。那这个叫做 beta expansivity， 这个叫做 kappa， 叫做 isothermal compressibility， 它都可以在实验中被量测出来的。那变成一个材料性质，那就把它写出来，就可以就是它可以适用在这个上面。Okay, so I guess I need to give you a break. After I will see you after 20 minutes. If you have any questions, just come here, and I will try my best to help you. Thank you. 好 ，OK。我签了。应该这样。但是我要先讲一下，就是如果今天我同意，但是我们系上，在申请的时候，可能就是说，哦，可能别的学校，哇，他们问过了啊，问过就好多，我只是怕说，我其实真有其他的规定我不知道，对，但在教学来说我 OK 的，这样好，谢谢。如果你没有问过的就 OK 了，好，谢谢。哎，请问，我是说的那个，就是 PPT 的，哇哦，我稍微尝试一下，算，还蛮简单的。好，请说。我觉得他了解的蛮好，就是因为他说什么是一个城市，第二个我就不讲讲，那个城市工程师是很大的东西，那这个有解释到，因为他有说像A 字，就是你的图方，是代表什么？对，好像他也不是说是代表什么，这个OK。当我别的嘛，我还有问，
后面好像就有点乱了。
哈哈
因为我如果说把它变成同时状态，那个线
，OK，
还可以有跟
嗯，
小会有或者会有不同，
对，
对对，
哦，所以你的意思是说，它可以给你最基本的定义，对，然后但是它却没办法给你更深入的比较啊，或者是因为跟实验比较的关系，
有可能没有
嗯，
就
那你确定他讲的是对吗？
我觉得
是对的，
this something but then as long as多头可能
对，这 last question，
so the is lower than
很好啊，
the confidence
好，很好，你这个讲的就对了，
the term B is in the long reduces the free one
好的，
is correct
都对啊，很好啊，
对对
真的蛮不错的，酷，好，谢谢，没有我才不厉害，这只是大家都会用的，来来，那好，谢谢你的 report，我们来加个小分吧，请告诉我你的号码，
313
313
613
613
044
044吗？OK，
还是老师
然后你是说它可以 give the basic definition, but not more comparison 吗
深度的，对，更深度的
？But not providing in-depth comparison and the concept, right? OK，谢谢，很棒，
老师
感谢。好，请。
是对，然后变成通用的数，
对，没有错，他就是用数学去找出它，嗯，其实也就是其实应该有其他的东西可以改变 volume，一定有，只是可能一不明显，二人类很难做到，可能啊有另外一种 radiation 你看它的光光，但是我不会，比较难做，通常都是用温度跟 P 来写。所以理论上来讲，比一可以等于这个东西加这个东西加这个东西加这个东西。比如说，我们视为 T 跟 P 是我们什么重视的两个含的那个参数，哎，大概是这样。那如果今天我们重视，我们改变 T，我们改变 P，它会怎么样变呢？就是靠这个斜率，然后那个斜率会跟材料有关，什么东西？ 好，对。就是这个 P 就是这两个 P 啊，后面那个贝塔 V 底 T 跟 minus 卡塔 V 底就是底 V 啊，所以底 bar W 在这里，底 V 在这里，这么长，乘上 P，所以其实呢把这个拿出来，花回这个方向。
哦，
对，这个 V 跟这个 V 是抵消的，这个 V 跟这个分母的这两个是抵消的，原因是因为如果今天没有这个 V 的话，这个数值会跟你现在这个 case 的体积有关。对，但是如果今天，对，就是你这就不能是材料参数，这个系数不能当做材料参数，也就是跟你当下的体积有关。所以如果今天是换另外材料，你要怎么样子？但是如果你今天量一个材料，就是你除上它的 V 的话，比方说你只要量这种值的，其他体积都不适用这个值，这是它的体积的，它是一个比值的，对，比值的概念，让它能变材料的。
I wonder why
Yes.
why we must study this reversible process. Because nature is irreversible, right? So the formula can be used in industrial application, right?
Are you asking why it should be reversible process, right?
Yeah.
What do you mean? What is your
Why we must understanding about the formula for reversible process? Because the nature, like the
Nature.
yeah, the industrial application is
irreversible? Yes.
Yeah.
Yeah.
That's why we don't
Consider irreversible, right?
or directly to irreversible. Why we
Okay. If we are talking about irreversible, yes, there will be energy loss inside. But we need to consider, we will consider irreversible later. Right. I don't know if I can show you now, but I hope I can find it. It should be here, I guess. Let me check. We will discuss this. Irreversible to be the second. Wait a minute. Here. Okay. No. Sorry. This one. Combine the first and second law. Reversible and dissipated word. Irreversible. Okay, so we in general, we will talk about this. So now we are currently describing a reversible part, and then we'll do the in advance to do here. Okay.
So when I'm in industrial, I will always go with the irreversible formula. Is right?
Yeah.
And the use of reversible process is to know the cup to get the efficiency better.
Yeah, of course, yes. So, you see here, after we combine first and second law, we will considering dissipating work. So after this, you know how to considering dissipated work. So if later in your industrial work, you know how to considering dissipated work, just adding one more term in this, it should be okay. So you can imagine that irreversible work, inverse positive is reversible work plus dissipated work. So we firstly I learn from ideal case and then go to the practical way to do that. So I guess that's what your question, I guess, right?
Thank you.
Any questions? I saw you raise your hand. Is that because you forgot to lower your hand? Or do you have any questions? Anyway, if you have any questions, just let me know or type it. All right, so welcome back. You notice that this projection procedure method is not ideal. You see, there's a long-term mistake from Apple. You see, here. You see here, 941. See, 941. So iPad after projection by QuickTime, which is what I do here, the clock is always 9:45. Okay, this bug has been there for almost 10 years. 10 years, I guess. I do this every time I think, oh, this is 9:45, 9:41, and then sometimes I will, forgot let you to have a break. You see, now it's 10:12, right? But it's still 9:41. You see that? Interesting. 就是这边有一个苹果长久以来都没有发现的 bug， 就是9:41。如果今天 iPad 连接到 QuickTime， 然后投影到荧幕上的话，它就永远都是9:41。然后我好几次被这个骗，然后就害学生都不能下课，这样。所以蛮有趣的一个事情跟大家分享。然后 anyway then how about the ChatGPT TA Thermometer? How about that? Is that I interact with it. Okay, it. Quite fun. How about you? So there's a students saying that he discussed he asked TA the thermometer expand the ideal gas equation and then the van der Waals equations and the definition of all these extra terms, and then it explained quite well. And then, however, if he asks further question about why the experiment curve is not identical to the theoretical curve, the teaching assistant cannot report that, cannot respond about more detailed, more in-depth comparison and concept. So this is quite good report. Thank you very much. And I encourage you to do anything with the teaching assistant. I guess you will learn from that. I also asked it to solve some problems by screenshot of the problem homework assignment, and then it actually gave me a lot of words and equations. It looks okay, but I never actually do it by myself. So I encourage you to do that and to see what will it give you. Okay? 我只是说这个 teaching assistant ChatGPT 的这个东西蛮好玩的，就是尽量去用它，然后它可能会给你错误答案，你甚至可以教他说，哎，这边是错的，他就会改哦，他会跟你道歉。那有的时候道歉，他会把对的改成错的，所以反正好玩啦，好，你就去玩看。然后我希望你告诉我他到底怎么样，这样子好不好？请告诉我。那我想要知道他的极限在哪里，越有创意越好，或者是他怎么样帮助你学习越好。那依据你给我的 report 的，我认为就是例如说，你 report 给我当然很棒，谢谢。然后，但如果你今天给我更多的资讯的话，我会给你更多的加分。这样，像刚刚同学加了1分，棒，谢谢。那像就我所知啊，有一位同学，我的实验室的因为我就叫我实验室的同学说，你要多做一点，你要多看一点啊，这样有点强迫他们这样。所以 我有跟他讲说，他有说有一些 idea，我就说那你要把它发布到 Facebook 上，然后他就说好。那如果到时候他发布了，请不要觉得说他是很爱 show off，他是被我逼的，好不好？他其实没有那么的，他其实很低调的，但是因为我叫他发布的，所以他才发布。所以我希望大家可以学习他，就是说，如果他发布了，你觉得对你有用，你也用你自己的方式去跟 ChatGPT 玩，然后告诉大家你怎么学，你怎么请他帮助你的。然后我希望大家都可以得到使用 AI 的能力，这样我觉得反而应该是未来更需要的。I just want to ask all the students to interact with teaching assistant, a ChatGPT teaching assistant, Thermometer, creatively, okay? And then please report to me. Depending on, I mean, if you report to me, you will have bonus. If you report to me in a really high quality of the response, to make us learn a lot from your response, I will give you more bonus. All right, and I hope everyone can interact with that to make AI help you. I guess the ability to ask AI to help you is the most important skill that you will have even in the future. Okay, so let's play. All right, so please let me know. Where is it? All right, so let's continue. So after we have a, sorry. Okay, after we have this equation is suitable for, we just assume that it's a reversible process. And it's, of course, it's general enough for the solid, even gas. But if we apply more condition for an ideal gas condition, what will it be? It will make the beta become simpler, and it will make the kappa become simpler. Why? Well, I can give you a quick calculation to help you to know that. Well, this is not important if you are good at it, math. Oh, by the way, mathematic techniques is really important in this course. Okay, I have heard that some of your senior student saying that this is actually a calculus in material science and engineering department. Yes, it is. Okay, be careful. If you forget how to do the calculus, you need to review it. All right. Later, you will use plenty of calculus technique. Very important. All right. So that's the reason why beta become 1 over T. If we apply ideal gas, PV equals MRT, and then, well, just very quick. Personally, I think GoodNote is the best annotating app that I have ever used. The second best is Notability. I spend a lot of money to learn that. I buy a lot of version of other app try many apps in order to get the best, a noting experience for you. And you notice that I always turn on this magnify region to write, because I found that when you write down in this area, you will get the best handwriting in the iPad. 就是说我花了好多钱，买了好多那个 Note 的那个笔记的那个 APP， 我也买了很多不同的就是 device， 然后我发现目前这样设定最好的Good Note 506最好的，然后第二好的是 Notability， 我觉得啦，然后这笔一定要打开这种巨大化的手写区域，这样它才会有最好的那种笔触当然这个笔触不是最漂亮，我之前觉得最漂亮的是好像有个叫做本部 writing， 我不知道大家有没有听过本部，有哈，但它的笔触可以变得写的字会写的非常漂亮。但是他就没办法支援这些有的没的，所以我只好忍痛割爱，就是忍痛不用它。不然的话，我非常喜欢他那个手写的字的那个笔触。Anyway, right. So if we apply ideal guess, so after this from now on, it's become ideal guess only. Okay, because you apply ideal guess rule. So your debug W become MRDT minus MRT dP over P become for ideal guess only. Right. Okay, so of course, after that, if you have this, you for an isothermal expansion, of course, dt become 0. So you have d bar w equal to minus this one. If you need to get a real actual value, you need to do the integration from pressure PA to pressure PB, and you can get this one. Easy. And if you do the for an isobaric expansion, which means that dP equal to 0, and you do the integration, this one, get that. So you see, for an isobaric expansion, P times VB minus VA, so you can see page 4, it echo the same results. 好，这一个 slide 这一页讲的就是，如果把前面那一页的公式它是很 general 的，如果更进一步的应用到 ideal guess 的话，那这些贝塔其实就会变得非常的简单，因为我使用了 PV 或者 MRT， 然后它就可以简化让 kappa 变成P分之一，贝塔变成 T 分之一，然后但是既然你 apply 这个数字了，这个公式以下都会是只有理想气体哦。那上面这个是没有问题的，是所有东西都可以。但是你一旦 apply 这个东西的话，就只能理想气体啦。然后用这个理想气体的话，你可以有2个方式，针对不同的项去做，例如说做实验好了。你在这边的话，就是你只做定温的变化，定温的体积变化的话，压力变化的话，那你的 work 就会是做积分就可以得到这个式子。那如果今天是定压的变化的话，你改变温度的话，你就可以得到这个式子。那这个跟第4页有关一模一样，我们都早就知道了，所以你可以去比较一下。Okay, example the pressure on 100 grams of nickel increased quasi-statically, which means that every step at equilibrium state, and isothermally, okay, dt equal to 0. From 0 pressure to 500 atm, and calculate the work done on the material. Okay, assume that density and isothermal compressibility remain constant at the value of blah, 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 respectively. Okay, so that's simply just do the math. Kappa PV dP W equal to minus kappa PV dP, because dt equal to 0. Why? Because isothermally, right? So W need to be do the integration, right? Minus kappa V and V and PB, PA, PV, E. Okay, and it should be minus kappa V divided by 2. PB2, PA2, and then it is 0. 0 pressure, from 0 pressure to 500 atm. So W means equal to, okay, minus 6.75 times 10 to minus 12. One over pi. So be careful about the unit. 100 gram. (8.9 times 10^3) kg m3 times 10 to 3 gram. Sorry, it should be, what's that? Oh, kg. Okay, then divide by 2, and then times 500 atm times 1.01, 10 to 5, ha to atm. So careful about the unit. Equal to. Yeah, did you notice that I didn't use the magnify region to write this. And you can see that the word I write here using magnify region looks better than this one, right? To me. Anyway, so you see, ha looks different, right? This is directly, I write this directly on iPad, but here I use a magnifying region. So it looks a little bit different. Interesting. See? Different. This one, this two looks better, right? OK， 好，这是一个例子。这个例子呢，它是就直接在公司里，然后isosermal 就底题就不见了，然后做积分。那这个地方需要注意的，其实就是我觉得啦，反而是那个什么，反而是单位转换1除以帕，然后 kg 除以 m3，然后不要忘了还要再做一个克跟公斤的转换，然后再做 ATM 转换，就这样。那刚刚顺便闲聊一下，就是说你有看到我最后这个地方是用直接在 iPad 上直接写，那这边的几个字都是用放大的区域来写，你就可以发现这个 pa 跟那个 pa 就写的不太一样。对，这都是我就觉得有点，就会让我觉得说哇，写的字好丑这样。那这边虽然有点乱，但是我觉得至少比这边好看的，可能是粗细的关系吧。Anyway, quite fun. Okay, so let's continue our lecture. Next page, we are going to discuss heat capacity. Heat capacity is important because we are talking about thermodynamics. Thermal are all related to heat capacity. Right, let's go. Maybe I need more. Maybe you need more time. You know, sometimes I will record my lecture and I will ask my mom to see that, to watch it. And my mom said, good, but she always did that. Good, but she always give me some advice, always. Maybe Asian parents always never think your kids do great enough. She always said, very good, but you just speak too fast. Your handwriting is too lousy. You're writing too fast. Yeah. So I don't know if do you think I'm speaking too fast or too slow? I don't know. I guess all of you can get used to 1.5 times speed in YouTube. So my speed is okay, right? 哎，听懂我刚才讲什么吗？我会把我的课堂录音给我妈看，然后我妈就会说，不错啊，但是她每次都这样讲，但是都会给我一些建议，这样，然后她永远都会给我建议啊，对，然后她就建议我说我讲话太快了，然后要讲话慢一点，然后写字太快了，太潦草了，要慢一点，这样大家觉得怎么样？但我觉得应该还好吧，你们都1.5倍速在看东西的。我这样子应该比1.5倍速要慢吧 ？OK 吧？也有可能是我上一个礼拜讲的，就是说人到了一定的岁数以后，那个就变得很慢，速度就是反应变很慢，所以我即使是讲正常速度，他都会觉得我讲太快，有可能是这样。Anyway, next, heat capacity. Heat capacity C is defined as the limiting ratio the heat absorbed divided by the temperature increase. It is not a derivative. Oh, this is really important. Not the derivative, although it looks like one. C equal to the bar Q divided by T. Okay, you see, This is the bar. This is the. It is not derivative. Derivative looks like dq, dt, but no, this is not. Well, this is not derivative. This is just simply divided by dt. Okay, so you need to be really, really careful about that. Don't do the differentiation. Okay. When isothermal C equal to infinity, of course, because 0. Your dt becomes 0 means that C become infinity. If this is adiabatic, 0, of course, simple, right? So extensive property, right? Because if you n increase, which means that your d bar q needs to be increased proportionally. So your C also proportional to your n, your mass, right? Because you have more mass, it will be more difficult for you to heat up this material for certain temperature increment, right? So typically we will make it specific. We just divide by n and we make it C equal to 1 divided by n, okay? And make it Q become small q. Temperature. Temperature is not related to n, so it's not affected on the T, right? So d bar Q become d bar small q. So typically we will measure. This is kind of a material property as well. We measure a material for their specific heat capacity under 2 typical conditions. You measure one value at a constant value volume. You may measure another value, obtain another value when you measure at a constant pressure. Okay, so they are all the property for that material. So CV, well, I will give you a small CV, well, defined by d bar Q, d bar T, dt, V, Cp, defined by d bar Q divided by dt at constant P. So you see that they are actually d bar Q over dt. The only difference is only the V and P, which means that you measure this value under different conditions. But both of them describing the same material, just the same material under different conditions. They will have different C, different heat capacity. So we name it CV and CP. They are related, okay? Their ratio of specific heat capacity gamma is Cp divided by Cv. It's material properties, okay? These are material properties. If you have specific material, you will have specific value of gamma, which means that you will have the same similar ratio of Cp and Cv. OK， 比热呢，它很重要，它的定义呢是，当你加热一个东西的时候，你给它的热总 total 的热除以它增加的温度 ，OK， d bar Q divided by dt， 哦，那这不是微分哦，这绝对不是微分，要小心。然后它跟n mass 成正比，哦，越大的体积，你就要花越大的热去增加特定的温度，这很正常吧，哈。那所以说，我们通常会把它除以它的体积，不对，讲错了，除以它的质量 n， 然后就让它变成小写的 q， 因为 t 跟质量没有关系，所以它对它没有影响 ，n 是给它的 ，OK。然后呢， 写完以后，我们就可以发现，这是一个材料参数，同一个材料，你在不同的状态下量测它的 specific heat capacity 的话，你会得到不同的值，但这两个值都是在描述同样的材料。那第一个是在定体积下量测的，它就会是 Cv， 在定压下量测的就会是它的Cp， 然后它们两个有一定的比值伽马。之前同学有曾经问过说这两个值就是他搞不清楚，就是为什么同一个材料会有两种不同的值，那表示说你是用不同的方式去量测它的，所以它当然会有不同，就好像你白天的状态跟晚上的状态不太一样，但都是你嘛，对哈，大概是这样子。然后我那时候很难去跟他解释，就是很难去解释。我那时候竟然情急之下搬出一个东西，说就像蝙蝠侠，白天是布鲁斯韦恩，晚上是蝙蝠侠，然后他听不懂，然后我想，哎，那怎么办呢？啊，我不知道大家听不懂我刚才讲什么，但是我那时候有时候同学问我问题，然后我就会，如果无法当下回答的时候，我有时候会狗急跳墙，反而越解释越难懂。我觉得有时候对，蛮有趣的。Anyway, so let's continue our lecture. Specific heat capacity Cv and Cp. Let's write down some information, obtain some information by using math. Math is always a really good tool that can help us to obtain or discover, reveal the underneath concept. For example, if it's something you don't know, but when you try to write down the math equations, sometimes you will find the underneath concept. This is what we are going to do here. Right, so that's the reason why they say math is the mother of the science, right? So constant volume, constant pressure, the definition of Cv and Cp. So for a reversible process, we set that at page 9. du 这个地震，糟糕了！我觉得我昨天晚上就是在家里的时候，忽然就有一阵晕眩，然后我就想，哎，我是要中风了吗？但我那时候我太太说好像有地震，昨天晚上有地震吗？没有哦，糟糕，那真的都看。然后我刚才也忽然觉得，怎么好像有点摇晃？然后没有地震啊，糟糕！我等一下记得帮我叫救护车。怎么会这样？我刚忽然觉得，怎么开始有点摇晃 ？Anyway, right. For a reversible process, P9, we discussed it before. Du equal to d bar Q minus TdV. Okay. 刚真没有地震吗？我靠 ！Specific heat, a specific term. So in page 9, we have capital U, du, capital Q, d bar Q, PdV, and we go for specific term, right? The small u, d bar small q, ddV, right? And then we know that du is nature. It is nature to choose u as function of v and t, right? So we can say, okay, du has two contribution, dv contribution, dt contribution. This is the slope, right? Slope. Okay, so I said u can be treated as u as function of v and t. Okay, so by the way, the symbol in my lecture note here, the dashed line, gray dashed line, is that something we learned before. Okay, something we learned before, you should know that, and then we will use that in this page. Okay, so I won't go through much detail in the content inside this gray dashed line box because we talked about that before. OK， 这样听得懂吗？我说以后啊，看到这个灰色的这个虚线，表示说我们已经讲过，看到它，我不会讲太多，因为我们已经讲过了啊。OK，so just recognizing, try to get used to the symbol I used, right? Okay, so if we substitute this into du, and then we will see that okay, so we just substitute this, and then we can find that this p and partial u over partial t, they all under dv. They are all the coefficient of dv, so they can become together here. All right, so you can imagine that this stuff go to the left hand side, d bar q's here, and then this stuff become here, and this stuff combined with this. Okay, right. So then, luckily, constant volume. Then, okay, so we can conclude that CV equal to partial U over partial T at constant V. Okay, so CV equal to partial U over partial T over constant V. Right, again, you see that we borrow the power of the math. And then we found that, oh, CV is actually a partial U over partial T V. So if we know the partial U, and then we can get, and then T, we can get CV. Okay, so again, underneath knowledge can be revealed by the math. Beautiful, elegant. Okay, and then let's talk about constant pressure. Constant pressure definition, Cp equal to d bar q over dt at constant p. Then for an ideal gas, Gay-Lussac experiment conclude that this one, partial U or partial V of at constant T equal to 0. Okay. I know that this is, well, just accept it. They do the experiment and then they have their own conclusion saying that this term equal to 0. For now, I would like to ask you to accept that, but I will prove that. I will prove that in chapter 5. Okay, so now at the stage you accept that. Okay, later I will prove that. So if this one for ideal gas, this one equal to 0, this one equal to 0, I will prove that later. Okay, now at the moment you just accept that. So if we make it 0, and this become d bar q equal to cv dt, cv, right? Cv dt plus pdv, this comes to 0, right? So this go into here, no problem. And then we can further make it the pv dt equal to the RT dt, and then so P dV equal to plus V dP equal to R dt, and then we can substitute up here, and then d bar Q becomes CV plus R dt minus V dP. All right, then we notice that CP plus CP equal to CV plus R. Well, you can see that constant pressure, right? Constant pressure, 0. So d bar Q equal to CV plus R dt. If you take this to the left-hand side, you can have this CP definition equal to CV plus R. So this is called Mayer's equations. Okay, so based on the math tool that tell us CV and CP relationship, and then now I would like to write down something here to do the kind of summary in this page. D bar Q equal to CV dt plus P dV. Sorry, should be small. And then D bar Q equal to CP dt minus V dP. Okay, so I will using a pink box highlighted because we will use that later. All right, where does it from? Here. Well, this one. Okay, and this one. All right, so do the summary for this page. 2 equations here. We will use that later. All right. 好，那现在要讲中文，就是我们要用数学的方式去帮我们去解开、找寻 CV 跟 CP 底下我们未知没有看到的知识关系。好，我们就来找找看，这是他们的定义，没有问题。然后我们第9页得到这个，但是我们把它写成比参数啊，比参数除以 n 变小写啦。然后 du 呢，我们可以把它写成2个共线 v 跟 t 的共线。然后这边这边讲过了哈。总之我们就把它摊进去，然后我们把黄色部分 dv 这个项综合在一起，就变成这样子啦。那这样子以后 dv 为0 constant volume 嘛哈，然后就得到这个关系式，结束，左半边结束了。右半边怎么办呢 ？constant pressure 得到这个，这是它的定义。但是这边呢我们把这个是借过来用，这边可以用哦，因为这边是很 general 的嘛，是一个一般性的式，我们把它借过来用。但是啊，这边可以跟大家讲一下，就是 Gay、Lussac、Joule 应该是3个人吧，应该是3个人吧。这3个人做的实验，我也不知道什么意思啊。总之他做了一个实验，他发现，在最佳气体理想气体状况下的时候，它的 partial U over partial T at constant T 会等于0。那也就是说，这个式子的这里面这个项会等于0。但是我们要怎么样？就是目前啊然后就是做一个实验，得到这个结论。但是我们其实可以去证明它哦，我们可以证明它。那证明它，我们在第5章的时候会证明，好吗？所以你现在先接受它，好不好？等一下之后再证明。这个等于0， 等于0以后，这个式子就变成这个式子啦。那这个式子呢的 P 又可以继续写下去，写下去完以后呢，就可以得到这么漂亮的式子。那 P 是 constant， 所以这边等于0，所以只剩下这个东西啦。这个东西抵 T 拿到左边去，就知道 CP 这个定义呢会等于 CB 加 R， 然后这是著名的 Mayer's Law 啊 ，Mayer's Law。好，得到两个公式以后呢，最后我想要把两个式子做一个总结哦。我们把这个式子，应该说从这边呢，哈，拿过来的这个式子放到这里，然后呢，这个式子把它拿到这里来，用粉红色的荧光笔标注出来，等一下我会用到。All right, so let's continue. 3 minutes. Continue our lecture, enthalpy and heat of transformation. Okay. Enthalpy is really similar, really related to heat. Phase transition. Phase transition. A phase change is typically an isothermal and isobaric process. Remember the isotherm we talked about last time, right? Remember that. We have a V, we have a P, and we have an isotherm, right? Remember that. We talked about this last week. Isotherm. Okay? And you notice that when they have a platform, we have initial condition and final condition. Well, during this process, it is going to do the phase transition, phase change, right? So you see, this is the isothermal, and this is the this platform has constant P, so it is an isobaric process during this range. So phase change is typically an isothermal isobaric process, so and entails a change of volume, of course. So it can tell us again du equal to d bar q minus d bar w. Okay, that we know that for sure. Then we notice that u q2 minus u1 and d bar w p v2 minus v1, of course. And what is q? The q here, we write it down, is L. L is the latent heat of the transformation per kmol. Is equal to the difference in enthalpies of the two phases. Right, actually the L is the heat that needed during the phase transition. Okay, this is the definition of the latent heat, right? So L equal to, put this to the left hand side, U2 plus PV2 minus U1 plus PV1. And then we define this as a enthalpy. Okay, so in the Chinese word enthalpy, H defined by U plus PV. Okay, and then I guess I need to give you 10 minutes break, and then if you have any questions, just let me know. See you after 10 minutes. Thank you.
结束了吗？因为卡法它是有 P 的那个 variable 在里面。
OK，
就是你刚刚算的时候把它当做常数。他说什么啊？assume 它是 constant，remove constant。
哎，
还有人，
好险，我很怕。对，它其实上面有写。 Hmm. 喂，Welcome back。刚刚啊，收到一封信啊，就说啊，就是要请老师们协助与支持学生申请心理调试假。他说，每5个大学生就有1人有忧郁的倾向，忧郁的倾向比例占25.5%。我真的觉得这是很重要的一件事情，因为啊，我们越来越聪明了嘛，忧郁是只有聪明人才会有的哦，我觉得啦，你看狗儿猫儿过得多开心啊，对不对？对啊，所以我觉得就是这个问题真的是越来越严重。然后我前阵子也蛮忧郁的，现在也没有好到哪里去啊。但是就我是说，以前40岁以前，我都觉得啊，生活很棒啊，没问题啊，什么什么的。就没想到40几岁以后，就觉得哎，可能就是所谓的中年危机吧，然后就觉得啊，就很不开心这样。那我才真的知道，就是说，忧郁真的是还蛮严重的一件事情，需要我们去好好的正视这件事。那我自己的解决方法，每个人有不同的解决方法啦。但是就是我自己的解决方法就是看书跟运动。那就心情不好，身材越好，就就一直去跑步，一直跑步，然后就就是反而因为心里不开心嘛，至少要让身体去扶自己一把。那当你的身体不好的时候，要靠心理强壮的意志力去扶身体一把，这是我自己的理论啦哈。所以说，如果你真的心情不好的话，就去跑跑步吧，然后逼自己跑步，多看一些书啊，那些书对于忧郁啊，是什么样的一个状况？就是说，它好像会你的脑袋里面有一个东西叫做不知道是杏仁核吗还是之类的，然后它就是会启动一个叫什么战或逃的理论，就当你遇到一个压力的时候，你要么去 fight，要么就去逃走这样。那但是现实生活中是没有在逃走这件事情。就是所谓的以前的逃走是指原始的状态的时候，狮子来了，老虎来了，熊来了，然后人就逃走，或者你跟他打战，这是正常的状况。但是现在不是啊，现在那种熊跟老虎不会出现，它出现的是比如说课业压力、人际关系等等等，所以你其实逃不掉的。但是你的脑袋又已经发警报了，所以长期下来就忧郁了。那我后来自己在那边跑步啊，有在乱想，你就在想，哎，搞不好你在跑步的时候是一种用实际的行动去骗你的脑袋，你其实在跑步嘛，你看你在逃了，你在逃离这个熊啊，假装的熊啊，或者是老虎啊之类的，所以脑袋就会过好一点，就觉得啊，我已经跑了，我已经逃了这样。我不知道啊，总之就是真的跑步对我来讲很好用啊。也需要人聊聊啦，所以说，如果我也不是叫你要跟我聊啦，我的意思是说，如果你需要忧郁的话，你可以找找你朋友啊，或者什么多聊聊这样子，然后多跑跑步，然后多看看书，看书也不错啊，看书可以。我以前觉得说看什么书啊，我书还念不够多吗？对，我后来发现还是要看书啦，然后我就买了很多电子书在我的手机里面。对，然后随时随地都排队的时候就看一下，然后无聊的时候看一下，还蛮有趣的，就这样。好，加油。然后很有趣哦，我以前呢，生涯规划老师都叫我去分享一些，就是有一堂课1小时叫我去分享。我以前小时候不是小时候啦，我10年前刚来学校，大概10年前左右，4、5年开始，我都在讲，大家要努力，大家要热血，大家要加油。 然后到了最近这几年，我就说，哎，也不要太紧张，也不要太逼死自己了哈，就适度就好，适度的热血，适度的努力就好啊，不要逼死自己。然后有的时候也要给自己喘息的机会。嗯，对，这就是人生不同的境界会有不同的，不是不同的境界啊，不同的状态会有不同的想法。Okay, let's continue. What I've discussed is that I just noticed that depression is a really big issue for generation nowadays. Me, you, everyone in this society. A lot of pressure come from different places, and then depression is really important. You need to pay attention on it, find a way to dealing with that. My personal experience is that going to do the sport, do exercise, jogging, and reading. It helped me a lot to face this depression. I hope everyone can deal with that seriously. Find a friend to discuss about that. That's it. All right, let's continue. So we just talk about definition of L. The L is the latent heat. That is the heat required during the phase change, right? And because of the L, we define that U2 plus V U plus PV as a H. It's an enthalpy. Okay, the enthalpy is the specific enthalpy is also a state variable because you see that what is the composition of the H? They are U, P, V is a composition of H, right? They are all state variables. So H is a state variable as well. Because they are state variable, so their cyclic process becomes zero as well. And it is nature to choose H as a function of temperature and pressure. Why? Because this is always under the isothermal isobaric process, under constant T and constant P. So in other words, if we specify the temperature and pressure, we specify the H, right? So that's how we define that. Enthalpy 含就是主要是在讲相变化的时候状态。相变化还记得吗？我们上周有讲到这个 PV 的 isotherm， 所谓的等温线。这个等温线在这个平台上在干嘛呢？相转变。相转变的这条线是 isotherm 等温线。那这个平台的时候又对应到一个定值 P， 所以说 phase change 通常都是一个相转变的状态，通常都是一个定温定压的状态。那这时候知道这件事情以后，我们就开始写这把它写出来，然后我们想要描述这一段，那这时候就是 U1 U2 相减会等于 L， 这个 L 什么？就其实这个 heat 啦哈，就这个底坝 Q， 这底坝 Q 什么意思呢？在这边的意思就正好就是要经过这一段相转变，它需要多少热，也就是所谓的潜热吗 ？latent heat， 潜热应该是吧？哈，好，然后我 L 就写出来了，然后这边的 P 就是这样，然后把这个东西移过去，然后我们就会发现 L 会等于这个东西这两个状态相减的差值，也就是说这个1跟这个2之间的有一个东西，它可以去描述第一状态跟第二状态，它们的差值正好就是 L。好，那这个东西叫做含，我们定义它 U 加 PV， 然后它会是一个 state variable， 因为 U、P、V 全部都是 state variable， 所以 H 呢当然也是 state variable。既然它是 state variable， 所以如果你做一个 cyclic 的 process， 初始跟结束都相同的话，它会为0。然后因为这条线是等温，这个平台又是等压，所以我们用固定的 T 跟 P 就可以 指派说 OK 这 H 的状态是什么，所以我们很正常、很自然的就会把 H 视为 T 跟 P 的函数。Okay, so let's continue. Internal energy U and enthalpy H. So, yeah, let's take a look. Remember what I said about the pink highlight, right? Pink highlight. Here, right? Pink highlight. Pink highlight. All right. So I just use that because we use the ideal gas PVT equal to MRT features into that. So of course this pink highlight is under in this row ideal gas. Okay. So let's correlate the CV, CP, and internal energy and enthalpy. All right. So in page 13. Okay. In page 13, well, 13 is oh, yeah, in page 13 is a highlight, right? This one, page 13. Right, and then let's start. We can substitute the bar Q to here, right? And then, so they can cancel each other, right? So we can have CV equal to partial CV, yeah, CV equal to partial, yeah. So that's how we get the CV equal to partial U over partial T, right? So this is what we learned in page 13. We know that, and we want to go to exactly the same process for enthalpy and the CP. Okay, so we are going to write down the definition of H equal to U plus PV. And then we also know that DH equal to DU plus VD, P plus PDV. Okay, and then if we get this to here, and then can obtain this one. Okay, right. And so if we substitute this to here, and then everything will go here because they will cancel each other. PDV? No. Sorry. PDV. Right. So they can cancel each other, and then we can get this one. Okay. Right. Then again, if we substitute from here, we can get CP is actually partial H over partial T, a constant P. All right. So you can see that this, we can obtain that by, in the page 13, we will use exactly the same procedure. We get CP equal to this one. So CV related to U, CP related to H. Okay. And then, of course, if we are to get the actual value of the difference of U and difference of H, we just do the integration, and we can get the difference of U and difference of H. 好，那我们现在要讲的就是内能跟 enthalpy H 跟 CV 跟 CP 之间的关系。那粉红色的 highlight 我们从第13页抓过来了，写在这里。然后呢，我们已经知道 internal energy U 会跟讲错了 ，CV 会跟 U 有关啊。那我们当时怎么做呢？我们把这个式子带进去，然后就可以相减，然后可以得到这个式，没问题。那我们现在要一模一样的方式来去做这件事情。那怎么做呢？我们先把 H 写出来，
然后再把 du 带过去，就可以得到这个式子啦。那这一样把 d bar 带过来这里，就得到这个东西了。OK， 所以我们就可以又再度用数学的方式去连接 CP 跟 H， 找到它们之间的关系 ，CV 跟 U 的关系。然后我们就可以借由量测，就是我们可以知道 CV 是多少嘛，哈，那我们就可以去算它的叫什么温差之间的温差，就可以得到它们的 internal energy 的就是内能的差值跟 H 之间的差值。如果你用 CP 来算的话 ，OK， 所以就这样。Next one. So now we can do a summary for work done in a process. For an ideal gas, we just do the summary, right? Most of the content in this page, most of them that explained that before. Okay, so this is just a summary. Don't be afraid. So work done in the process in the isobaric process. It will has W equal to P times V2 minus V1. We know that in page 4, right? And for the isothermal process, well, I don't know why I write down ideal gas twice, because I written down here before, redundant, okay? So W equal to RT natural log V2 V1 equal to V1 V1 natural log V2 V1. We've done that in page 10. And how about adiabatic process? Adiabatic process, we have two ways to look at. The first one is about CP, the other is about CV. So of course, the bar Q equal to 0, the bar Q equal to 0. So what will it looks like? It will looks like V dP equal to CP dt, and the other is P dV equal to minus CV dt. Okay, so from these two, we can divide them. Okay, if we can divide them, V dP, P dV equal to minus CP divided by CV, which is minus gamma. Gamma is the ratio, right? Remember that? So we can P over P equal to minus gamma dV over V, and then we do integration for that. Then we can have natural log P minus gamma natural log V plus a constant, integration constant K1. So if we can do further, natural log P plus gamma natural log V equal to K1, which means that P V gamma equal to K. Okay, so yeah, that's it. Of course, K1 and K are different, but they are constant. Okay, they are constant. We're just changing the natural log, get rid of the natural log, right? So, well, it's nothing new. You know this, right? But we just do some manipulation to make it, write it down, like, in a better form. So the gamma is the ratio of that. The K is a constant of integration, right? So that's it. And the work done in an adiabatic process. Adiabatic process, what is the work done on this? So it's PdV equal to, we just need to get this one to the right hand side to substitute this P. You can get this. And well, you don't need to remember that. You don't need to memorize it. All you need to do is understand this one, and then the rest of it, you can cope with that. You can use your mathematic technique to get this. This is not important, actually. Right, that's it. 好，我们要讲的是，我们讲了那么多功，那我们今天要把它叫什么？统整在这一页里面啊。那我们这 for idea guess， 那这边多写了一次 idea guess， 我觉得很丢脸，擦掉吧啊，就是冗，这个太冗。那 isobaric process 第4页就写过啦 ，isothermal process 第10页也写过啦。那 adiabatic process 我们也知道，就是要把这个底坝 Q 跟带进来嘛哈。然后等一下我看一下哦。对啊，你看这个东西不就是刚刚的 pink， 这里都是我们学过的嘛哈 ，pink highlight right pink highlight 然后我们就把这个底坝 Q， 因为 adiabatic 嘛哈，把它带进去等于0，就可以得到这些式子，然后再继续的步步的逼近。这个 CP over CV 是一个伽马值，伽马值就是它们的比值嘛哈。我们刚刚前面有讲到，它是一个材料参数哈。然后我们就做积分，就做到，结果做到一半就会发现它会有一个积分常数 K1。那因为它是 natural log， 我想要把 natural log 拿掉的话，这 K1 会变成另外一个值，它也是常数。既然 K1 是一个常数 ，K 一定也是一个常数，只是它们俩不同值。只是一个是有 natural log， 一个是没有 natural log。好，那这个东西记起来就好啦。那接下来要做的 work done in the adiabatic process 的话，就是直接把这个 P 去做积分啊。应该说这个东西是它的 work 嘛。那把这个 P， 把这个东西移到左边去，右边去，然后带进去，这样就可以了。来到这里 P， 然后做出积分就可以得到这个式子。不用背了哈，反正就知道这个东西就好了。然后 work 你就自己把它算出来就好啦。Okay, some example. Example: an ideal monatomic gas. What is monatomic gas? It is because it is a single atom type gas. For example, helium, argon, something like that. Single atom gas. Okay, it is enclosed in an insulated chamber with a movable piston for an adiabatic expansion. All right. The initial values of the state variables are P1 8 atm, B1 4 meter cube, and T1 400 K. Everything is in P2 1 atm. Find V2, T2, W, and delta U. Here, the ratio specific here for the ideal monatomic gas is gamma equal to 5/3. Okay, so let's continue. So firstly, we know that the same material, the same gas, they have different state. So, and also undergone adiabatic process. So which means that P1 V1 gamma equal to P2 V2 gamma. All right. So V2 equal to V1 divided by P2. 1 over gamma equal to 4 times A divided by 1, 3/5. 13.9 meter 3. Good. This写的还蛮好看的。All right, C2. I'm saying something good about myself, trying to give myself confidence. V2 V1 T1 1 over 8 13.9 400 1748. All right, so V2, like we get it, and T2, we get it. How about W? W, we have two solutions. The first one, just directly get this one. Okay. 1 over 1 minus 1.67. 1.013. 13.9 minus 8, 1.013 times 4 joule times 10 to 5, which is equal to 2.74 times 10 to 6 joule. Okay, this is a solution 1. Just the same as we mentioned in the previous page. Easy. How about solution 2? So solution 1 is kind of typical. We obtained from the previous page. The second solution is, how about we use gamma? Cp equal to plus Cv. So gamma equal to 5 over 3, which means that 5x equal to r plus 3x. So the x equal to r over 2. So which means that we can directly obtain Cv equal to 3 over 2r. And since Q equal to 0, delta U equal to minus W. So delta U equal to Cv times T2 minus T1. M3R2, T2 minus T1, P1 V1, RT1, 3R over 2, T2 minus T1, minus 2.74 times 10 to 6 joule. Okay, you see that? They are the same. However, they are in different sign. Of course, W, delta U, they are opposite side. Right, so you can see that, they matched, right? Interesting. So you can kind of help you to avoid do the integration. Well, integration. So you can get this right in the previous page. And then if you just directly obtain the delta U, you can also refer that you can get the W. Well, they are opposite. Right. Interesting. 好，要讲中文了。总之就是这个就是一个典型的一个例题，它是有单原子的气体，例如说氦气，然后就是一个英文字这样的一个符号这样，然后它从一开始的状态是 P1 到P1 V1 到P1 V1 T1 到 P2， 然后它请我们去算出 V2 T2 跟 W 跟 delta U， 然后他说它的 specific heat 的 ratio 是 gamma 5/3，那就对啊，因为它是 adiabatic expansion， 所以它两个点状态会是有这样子的关系，然后可以得到B 多少 T 多少。接下来 W 呢 suppose 你就可以用前面那一页去算出它，就直接带出来，值是 OK 的。那 solution 2其实应该这样讲了，你算了 W，你就可以算出 delta U 了。但是如果你今天假装不知道，你就用第二种方法，你从 CP 算出来 ，CP 算出来 R 加 CV 会等于伽马。那不是 CP 等于 R 加 CV 是长这样，然后你又知道伽马会长这样，你就可以知道 CV 会是多少啦。那你知道 CV 等于多少以后，你也可以直接使用 delta U 跟 CV 之间的关系，就算出它们之间的内能差。那内能差多少算出来以后，你就会发现它跟 W 是相反的符号。Alright, so that's it. I guess the review one, we have done the review one, and then I will give you some mathematical technique, some useful mathematical technique. The mathematical technique will help you to determine something in the next week. Okay, review 2. Okay, review 2. I believe here we have many things to write, so I need to give you some time. I will have some chat. Have some chat here. 我们要聊什么呢？前阵子有高中生老师叫我跟高中同学勉励几句，然后他就说：“老师，教授，请问你如果要告诉自己17岁的你自己，要跟他讲什么话呢？”然后那时候想了好久然后我终究还是没办法想出一个我真正想要跟我自己讲的话，然后我就说那就要多尝试啊，多认真啊，这样。我讲这种很八股的很烂，然后我就结束那一回合，我就回家了。然后当天晚上我就在想，我到底想要跟自己17岁的时候讲什么话呢？想了超久，我终于想到一个答案。我现在真的很后悔，我那时候不知道，应该说我那时候最后悔的事情，不知道的事情，我应该先跟他讲清楚，跟我自己17岁的讲清楚。什么呢？就是其实17岁的重地你知道你不能喝牛奶吗？你不能碰你的衣柜，打开的时候你要用吸尘器去吸你的衣服，你才不会过敏，你知道吗？我发现这两件事情带给我非常大的，就是如果小时候17岁我知道这两件事情，不能喝牛奶，我对尘螨过敏，这两件事情如果知道这件事情的话，我的人生会有非常大的不同，搞不好我现在就都不一样。你知道为什么吗？因为我从小到大就是受到过敏，鼻子过敏的这种痛苦，就是小时候那种衣柜里面的那种尘螨我都不知道，那时候不知道，我只是知道我每天起床我就是一直流鼻涕，每天上学就是一直流鼻涕，念书也是一直流鼻涕，然后大家都说，就是我的那个抽屉里面都是卫生纸，就是上课的时候卫生纸，馄饨一大堆，然后我妈就一直跟我说，你就是吃太多冰的，我没有，但是小时候也只能说好是我不能吃冰的，但是就是成天都在过敏。那后来我才知道我是对尘螨过敏，就是对那种衣服，而且我还去抽血去验我是对美洲尘螨过敏。你知道有另外一种叫做欧洲尘螨吗？我只对美洲尘螨过敏，我对欧洲尘螨没有过敏，奇怪吧？不知道什么意思。欧洲跟美洲有差嘛？总之我只对美洲尘螨过敏，然后所以现在我只要从衣柜里面拿出衣服，我一定都会用那个吸尘螨的机吸，把它存起来，再存起来，或者是我要拿吹风机去吹，把它吹掉，存起来，我才不会过敏。所以我现在就好多了。你看如果我17岁甚至12岁我就知道这件事情的话，我搞不好联考可以多几分，你不觉得吗？我每天都在念书，一直在流鼻涕一直在擤写就会擤鼻涕，写就擤鼻涕。你不觉得如果当时知道这件事情 我可能念书会念得更好。再来第二件事情是不能喝牛奶，就是大家应该也看到我皮肤不是很好。我小时候就是一直长痘痘，一直长痘痘，现在也是一直长，但现在比较好一点。原因是什么呢？因为我喝牛奶，喝牛奶我的肚子就不舒服，虽然没有到拉肚子的状态，但是就是不舒服，不舒服，肠胃躁动，我的皮肤就一直长痘痘，这真的是完全连贯。所以，所以从小到大就是，但是我很喜欢喝牛奶，因为我觉得哦奶很香，很好喝，所以我就是一直皮肤状态都非常非常差。所以到了28、29的时候，我才知道哦，原来我有乳糖不适症。其实我跟你说，在座各位有70%的同学应该都是亚洲同学，都是乳糖不适症。然后我就觉得很奇怪，最近哦，真的是最近，益美才出了无乳糖的牛奶哦，喝了就没事哦。然后我就不懂为什么这么多年来研究指出亚洲人有70%是乳糖不适症，但是到最近才出了乳糖不适症的牛奶。我觉得台湾人就是很奇怪，而且我也常常听到就是说啊，喝牛奶就拉肚子，没关系啊，怎么会没关系？怎么会这样子？哦，所以我觉得很奇怪。在最近一枚卖无乳糖之前，我都得去好事多买那种无乳糖的牛奶，美国人出的。美国人的乳糖不是真的比例比我们还要低，但他们却有，我们却没有。我就不懂我们台湾人在干嘛，我觉得很奇怪，我很生气这一点。总之就是这样啊。那总之啊，就是希望大家多了解自己，搞不好你多了解自己，多做一些实验，发现为什么会肚子痛啊？为什么我皮肤会一直长痘痘啊？为什么我会流鼻涕？要找出原因来哦，不然的话，不要就让它得过且过，困扰你十几年，对你人生会产生很大的影响。这样子，对，这就是我希望大家要认识自己。Okay, I just want to let you know that everyone should know about yourself because to me, until 30 years old, before that I didn't know that I cannot drink milk. I cannot. I'm allergic to some some bugs. Maybe I don't know. I'm eligible for something. So if I knew that before, maybe I will, you know, I will have better life. I guess more healthier, more healthful body. I guess. Right. Just saying that. Okay. Next, some useful mathematic techniques. First of all, cyclic rule. Cyclic rule is another mathematic techniques can help you to find the underlying correlation between the parameters. For example, if you have a three variables containing in your consideration, three variables, and then you have one equation, all right? So which means that you have two independent variables. Okay, so for example, if you have a function containing x, y, z variables, and this function equal to 0 means that you have one equation. Okay, so one equation, then you can say your dx, your change of x, can has two contribution from dy and dz. This is slope, obviously, right? Similarly, your dy can also written down as dy equal to partial y over partial x dx. Also they have the dy has two contribution as well, partial y over partial z x d z, right? Similarly, so you can substitute here. And then you can get this one ugly form. Okay? And then you notice that dx. Okay, let's go to the left-hand side. And then you can have this ugly form again, which is dx dz equal in the middle. Right? So now, how can we solve it? You notice that dx and dz is a change of dx, change of dz. So actually, dx and dz can be any values, right? Which means that you can change dx, you can change dz whatever you want. But what kind of condition can make this equation held all the time, but dx dz has any value? The only way to make this equation held all the time is the coefficient equal to 0, right? So how about that? This becomes 0, this becomes 0. It looks like this. And what will it lead to us? This leads us to partial x, partial y, z, partial y, partial z, x, partial z, partial x, y equal to -1. Okay, so that leads us to the rule, cyclic rule. Okay, and we will use this in the next week. Oh, sorry, next week. No lecture in next week. Please let everyone know. Okay, right. Cyclic rule 就是循环的规则。假设你有一个系统里面有三个变量，然后它们之间有一个关系，使用一个式子来去描述它，表示说有两个独立变数。好，那它写出来了以后呢，它的 dx 会怎么样的？就是你改变 dx， 其实是应该这样讲，你要怎么样改变 dy dz， 然后它会让它 dx 也改变呢？有两个贡献 ，dy 的贡献 ，dz 的贡献，它的斜率，对不对？那写出这个式子以后，我们用同样的方式也可以把 dy 的写出来，代入进去以后，得到这个大式子，很丑。没关系，我们把 dx 放到左边去 ，dz 放到左边去，我们来相等。结果发现呢，这个式子它一定成立嘛，对不对哈？但是你的 dx 跟 dz 是 x 跟 z 的改变量，它可以是任何的改变量啊，对不对？所以说，如果今天 dx dz 有任何的改变量，都可以让这个式子完美的永远都满足的话，只有一种状态，就是它的系数为0，只有这样的状态，不然的话，你 dx 都可以随便调啊，那怎么会有等于0呢？怎么会相等呢？一定是它的系数等于0。好，那这个等于0的话，会得到这样的式子，这个等于0的话会得到这样的式子。好啦，所以说到最后你可以得到用这个来得到下一个式子，就是它们互相 xyz 这样子就是相乘以后会等于-1，这样子的式子我们之后会用到它。All right, next one. Oh, this is a little difficult. If you learn engineering mathematics well, I believe you can understand this one. If you are not, it will be a little bit difficult here. Right, integrating factor. Integrating factor is that can we make a non-exact function q become exact by multiply a factor, the factor called integrating factor. What does that mean? Non-exact function. Non-exact function means that depending on path right? Depending on path integration. The integration depending on the path. Okay. If we can multiply something to make that exact, means that it turns into another function that is a state variable, independent on the path. So we are going to see if there's any integrating factor A times Q as a function of xy, and it equal to, it becomes z. The z is also, of course, x and y function. And we want to see if this z can be exact. Okay? So what is the condition for the differential z is exact? If we successfully choose a good integrating factor A, make the Q become a Z, and this Z is exact, what will it be? What will the Z looks like? Okay, let's take a look. So if the differentiation dz xy equal to something dx something y, okay, obviously, of course, this m and m always the function of x and y. So what is the condition for the differentiation z is exact? Of course, we know that, right? If you do the cyclic integration to dz, it will become 0. If it becomes 0, which means that z is exact, right? So let's take a look. If this one becomes 0, what will m and n look like? Okay, so let's take a look. So this is x, this is y, and we do the cyclic integration. Let's give us a really simple cyclic one. We just do this cycle. C, okay? This C, this C is a cycle, okay? Cyclic procedure integration. Let's divide it. You see dy. If we do the cyclic integration, it must be doing this, right? And then this is related to dy. This is related to dx. So dy must be related to this path and that path. Changing y, right? And m dx cyclic integration must be related to this one and that, that one, right? So here we can say n here, the cyclic integration can be written as from C to D, n, which is a b y dy plus d to c and a y dy. And all of you know that this is green part. This is pink part, right? And I guess I don't have time to do that to finish this. I guess this is kind of difficult, so I will talk about this again in the next week. Okay, next week we don't have lecture. All right, sorry for that. I need to go to the American. Okay, America. Okay, so if you have any question, just come here, and then I will see you next week. Thank you. Bye bye.